is by far the easiest type of algebraic limit that you are going to do. When you have direct substitution, let me turn the pen on right here, you just plug the number in. And if you can plug the number in and you get an answer, that is your answer. You don't have to think about it in any more depth. That is the answer. So like, for example here, for this first one, to do this limit, you're just plugging in 2 to see if it works. So you're going to say 3 times 2 squared minus 4. Be careful right here. What have you got to do first? You got to square. So that's 3 times 4 minus 4. If I had let you all try it on your own, somebody in this room would have done 3 times 2 first and then squared it. I feel almost certain. And then we'll get 8 for that. As long as you get an answer, that is all you do for that. So if you're getting a number answer, you are good. Like example 2, you are just going to plug in -2. Square root of 6 plus -2 is going to be the square root of 4, and you get 2. There's your answer. Okay. 3 is so easy it's hard. What is the answer for 3? What makes 3 weird here? There's no x, right? There's nowhere to plug in that 0. So you can't plug in the 0. It does not matter what x is approaching here. The answer is just 5. Because if there is no variable for you to plug that number in, you just don't plug it in, and you get whatever is there. So this could be x approaches 10, it could be x approaches -7, it could be x approaches 1,000. You're still going to get 5 for the answer there. So it's kind of funny because these are like, should be no problem for us, you know, up here in varsity math class here at Elkin High School. These should be no problem. You might make a little mistake every once in a while and forget some, but like, these should be easy. Sometimes these are the most missed questions on a quiz or test that I give. The reason for that is obviously we're not going to spend much time on this because it's not hard. But we're going to move on and we're going to like do all of these harder situations. So whenever I throw something that like this at you, you start trying to do what we did for the hard questions, and it doesn't work. And then you just think you can't do it, and you're doing something wrong, and you don't get an answer or you guess. But this is what you want to try first every single time. You can do it in your head a lot of times, depending on how difficult it is. But you want to try this every single time, because if there is an answer, this is your answer. You don't do any of this harder stuff I'm getting ready to teach you. This is it. So don't forget about it, although almost guaranteed somebody's going to forget about it and miss these questions on the quiz or a test. So direct substitution can fail in 2 different ways. So the first way that it can fail is that you get something where the limit does not exist at all. Okay? And that will look like this. This is a simple example of what this would be. So if I try direct substitution here, I would get 3 over 0. And 3 over 0 is undefined. It doesn't give me an answer, right? So if you get something like this, if you get, if direct substitution gives some number other than 0 over 0, the limit does not exist. Okay, so this one, instead of putting equals D and E, I'm going to put like an arrow here and put D and E, because technically you don't say something is equal to does not exist. That seems silly to like say it out loud. It implies that the limit does not exist. So I'm probably not going to count off and put equal sign instead of an arrow, but arrows are better in that situation. Okay, so you get a number over 0, you're going to say that limit does not exist. That's going to happen sometimes as well, but not that often. The questions I'm going to ask you about most often are going to give indeterminate form. Okay, and here's what that's going to look like. If I try to plug in 5 right here, because direct substitution should be what we try first every time, I will get 5 squared minus 4 times 5 minus 5 over 5 minus 5. And that is going to give me 25 minus 20 minus 5 over 0. And then, again, I'm not going to use an equal sign here. I'm going to use the arrow for this as well, because technically, right here is I'm getting 0 over 0. Technically, nothing can equal 0 over 0. 0 over 0 does not equal 0. It does not equal 1. It is what we call the indeterminate form. So this right here, if you get 0 over 0, this is indeterminate form. And it's sort of nonsensical. If you think about what division means, like here, if we have 3 divided by 2, I have 3 cookies. I'm trying to split it amongst 2 people, right? That kind of makes sense. If I have 3 and I try to divide by 0, I've got 3 cookies. I need to put that in 0 groups or 0 people. Like, you can't really do that. Somebody's got to have the cookies, right? Like, they exist, so you can't really do that. So that can't happen. But if I have 0 cookies and I need 0 groups, that kind of sounds possible, but like also is like you're not getting an answer for that either. So this is an indeterminate form, and it means that we need to try another method, okay? Because there might be an answer to the problem. It also still may end up being does not exist, but we just don't know. Indeterminate means we cannot determine anything from it, and we need to try something else. So if you get 0 over 0, that is not your answer. That means that you need to try something different. Okay? So today and tomorrow, we're going to spend the majority of our time looking at some of the methods we can use whenever we get 0 over 0. Yes?
What about the, like, 3 over 0 situation?
No, 3 over 0, do not try anything else. Your answer is does not exist. So if you get any number besides 0 divided by 0, that's an automatic does not exist. So if you get that, you can feel like relieved. Oh, I don't have to do anything else. This one is just does not exist. But if you get 0 over 0, you got to try something different for that. Also, let's add this in here. Quick little note. Infinity over infinity is also indeterminate form. We do not run into that as much. There are other types of indeterminate forms you can have, like infinity divided by 0 and things like that. But in this class, the only 2 that you might run into are 0 over 0 and infinity over infinity. And we won't see this any today, but we might moving forward, and we'll look at that when we see it. Okay, so let's look at our first thing that we're going to do. I have this formula for factoring a difference of cubes up here for our example 5. I can't remember if we did this in pre-cal. I don't think we did. It's for example 5 because you don't know how to factor this yet, and I'm throwing it in because our textbook throws these types of problems in there, and it can't hurt you to know how to do it. I've not really seen one on the AP exam before, but it couldn't hurt you to know how to do it. Sometimes you might get a crazy Calc 2 professor that expects you to know already how to do some of these little things I throw in here, so it can't hurt to have seen it before. But example 4 is one that we should be able to do pretty easily. What we're going to do on these is we're going to factor and cancel. Now, the first thing, again, that we're supposed to do is we're supposed to try direct substitution. So a lot of times you're going to do this in your head, or if it's calculator active on a calculator, but I'm going to try plugging in -2. And I'm already seeing a 0 in the bottom, so this is not looking good. I'm getting 4 plus 6 minus 10. That gives me 0 over 0. So direct substitution has failed. Right? I can't do it. But one of the methods that we're going to try is factoring and canceling. Because probably what's happening here is we have a hole in the graph. If you remember from math, well, I think you did this a little in Math 3, but we definitely did it in pre-calculus. We looked at places where you could have holes and vertical asymptotes in a graph for rational functions. So, like, I would know, since there's an x plus 2 in the bottom, -2 is going to make that 0, and I can't divide by 0. So I either have a hole or a vertical asymptote on this graph. And to know which one it is, I need to factor. So if I do this, if I factor x and x, if I factor that numerator, I got to multiply to give me -10, add or subtract to give me -3. So that's going to be a -5, a +2. This is going to be over x plus 2. Some proper notation here. You do not get rid of limit notation unless you have plugged the number in. Right? So we still have x's. We have not plugged the number in. So we have to keep writing limit as x approaches -2. Now, right here, I didn't write limit notation because I plugged the number in, but it failed. So, like, I could mark that out. We're done with that attempt. It didn't get us anywhere, right? So I've got my limit notation. Now, I've got an x plus 2 on the bottom and an x plus 2 on the top. Those are going to cancel out. What does that tell me about the graph of this function if it cancels top and bottom? That's a hole, right? Canceling was a hole. If it didn't cancel, it would be a vertical asymptote. If it's a vertical asymptote, that's when you start getting like positive or negative infinity, or does not exist for those there. But if this cancels, it's probably a hole. And a hole, can we still have a limit at a hole? We can't, because it doesn't matter if it's an open circle or a closed circle. Limit is what you're getting close to. So we've got a hole in this graph. So I'm going to cancel these. This is going to give me the limit as x approaches -2. Now I've just got x minus 5. You can put it over 1 if you want, or it's in the top, so it's just x minus 5. And now I can do direct substitution very easily right here, right? -2 minus 5. Notice here is the first time I dropped my limit notation. I don't have limit notation whenever I plug in that -2 for my x, and then I get -7 for that. Okay? Yep, so -7 is my limit. Yep. Okay? Example 5. I don't believe we've done this. I don't believe we factored a difference of cubes. And like I said, I haven't really seen it on the AP exam, but our textbook throws these in there pretty often. So I want us to see it in case we end up doing some of those problems. The formula for factoring a difference of cubes is that if you have a cubed plus b cubed, I really shouldn't have said difference. I should say sum or difference here. If I have a cubed plus b cubed, I can factor it like this. It would just be regular a plus b. Sign stays the same in that first parentheses. And I will have a squared minus a times b plus b squared. Okay? So, let's look at how we could factor here. And then for the minus, it's just the signs. That first sign is the same. The second one is different. The last one's always positive, right? Mm-hmm. Oh, that would kill a lot of math fairies if you did that. Can I? Oh, it would be a math fairy massacre. Because, like, if you did that, if I cancel this x and make that a square right there, how are these things separated from the rest of the stuff? Addition or subtraction, right? I cannot cancel that because I cannot cancel these whenever there's addition or subtraction there. If it was x squared times something, I could, but I cannot cancel it. Okay, all right, okay. Using your logic, 3 minus 1, let me use a bigger number to make sure I don't get one that accidentally is correct. 6 minus 1 over 5 minus 1, using your logic, equals 6/5. Is that correct? 6 minus 1 over 5 minus 1 should be 5/4, which is not 6/5, right? So, when there are plus or minus signs, we cannot cancel. Right here, yes, there were some plus or minus signs, but not between the things that we were canceling, right? Right here, I had multiplication in between these two things, and I was canceling an entire term that matched on top and bottom. I was not taking just those 2's and marking them out. I was doing that whole term. So you cannot cancel right here. It will give you the wrong answer, for sure. Unless you maybe like just get lucky on something, but if you try it on every problem like this, you'll definitely get the wrong answer. Mm-hmm.
So what if you like pull out both x minus 1, and you get x over there?
You can't pull an x minus 1 out of that top. Mm-mm. So you have to factor it this way. Like if you if you had an x instead of a minus 1, like x cubed minus x, you could factor out an x and maybe cancel something there, but we can't do that here. And I forgot I shouldn't have marked this out because it was wrong, and this thing does not let me erase. But this is to the third power here, and we got an x right there, right? So you have to do it, even though we're trying our best to get out of it. You have to do it. So the way it works, we already have an x cubed. So like where we got this a right here, instead of a, I'm going to turn all those, oh wait, let's use the bottom one because it's minus. That's really like an x cubed, right? So that's going to be an x, that's going to be an x, that's going to be an x, right there. All my a's are really x's, right? The 1 is not cubed. But what is 1 cubed? 1. So could I put a cube right here and it still be the same? Now that wouldn't be the case for any other number, but for 1, it works, right? So that means that my b is really 1. So I'm going to turn all those b's to 1's right there. So when I factor this, it's going to look like this. I'll have x minus 1, and then I'll have x squared plus, I got x times 1 right here, which is just x, and then I got 1 squared, which is just 1. And so now, this stuff is multiplied by the other stuff there. X minus 1 matches the whole denominator the same. I can cancel those out. Like that. Which means now I'm doing the limit as x approaches 1. All I've got left is x squared plus x plus 1. I know this is going to work with direct substitution because there's no denominator. I can't get 0 over 0 for this. So I'm going to now plug in my 1. 1 squared plus 1 plus 1 is going to give me 3. So the answer for that one would be 3. You won't see a lot of that having to factor the cube, but it's going to be sprinkled in every once in a while for that. Most of it's going to be factored like this right here. All right, so we have not gotten to the rationalization part, which means I need to adjust your assignment. So let me look at these and see. I know you can still do 9, 15, and 25 because those are direct substitution. Let me see what I need to do to the rest of it. Let's see, 80, 51 through 60. Stop at 56 because we didn't get to the rationalization part of it. So 9, 15, 25, 51 through 56 is going to be your assignment. You can take your book home if you want, or you're welcome to get your phone and snap a picture of that, so you don't have to take it home. Either is fine. You guys probably have hardly ever used a textbook before. I realized this last year. Here's something important you need to know. Most math textbooks have this part at the back where it says additional answers. The answers to all the odd problems are in the back of the book. So in addition to taking a picture of the page that you need, if you flip to the back of the book, this is assignment 84, on page 84. So you got to kind of flip around. I like to keep myself a sticky note in the back of my book so like I'm close to where I'm supposed to be. Let's see. Where is it at? It's AA11 is where the answers. Why doesn't? Oh, no. Yours is different than mine. But the back.
Oh, wait, the numbers?
Yeah, dude. 9, 15, 25, 51 through 56 are the numbers that you're doing. But